Okay, if you remember from last time, the linear programming problem involves the cost function, equality constraints, inequality constraints, and positivity constraints. But in order to actually solve it, and other than very simple problems as we had in the last video, we have to convert the inequality constraints into equality constraints. So we call this the standard form or the normal form of a linear programming problem will involve the cost function or objective function, the equality constraints, and the positivity constraints, but no inequality constraints. So we need a way to convert the inequality constraints into equality constraints. And we do that using what are called slack variables. So let's illustrate how we do this for just one inequality constraint. So let's say the inequality constraint we have is x1 plus 2x2 has to be less than or equal to 5. So we can rearrange that. We can bring the left-hand side over to the right. And then I'm just going to flip the sides. So 5 minus x1 minus 2x2 has to be greater than or equal to 0. So now we have an expression where it's 0 instead of 5. Fine. So what we do is we define a new variable. We're going to call it S1. It's the slack variable that corresponds to this inequality constraint. And S1 is equal to 5 minus x1 minus 2x2. So what that's saying is rather than saying 5 minus x1 minus 2x2 has to be greater than or equal to 0, we can simply say that S1 is greater than or equal to 0. And you'll see why that is advantageous then in a second. So again, this is basically what we say is we say that S1 is taking up the slack available in the quantity that is represented by this inequality constraint. So for example, if S1 happened to be equal to 0, then that would mean that x1 plus 2x2 was actually equal to 5, such that there was no need to take up any slack. So that's the basic idea. So let's go back to 620. The original inequality constraint, x1 plus 2x2 is less than or equal to 5. And what that says in terms of the slack variable is we can turn that into an equality constraint by simply adding s1 on the left. So if x1 plus 2x2 is less than or equal to 5, then there's some number s1 that quote unquote takes up the slack such that x1 plus 2x2 plus s1 is now equal to 5. So that is our equivalent equality constraint that's equivalent to the inequality constraint we had here in 620. Then we also have the positivity constraint that the slack variable has to be non-negative. It has to be at least 0, so greater than or equal to 0. So for every inequality constraint that we have, we're going to introduce a new variable, a new slack variable, and that converts the inequality into equality constraint, and then we're going to add in an additional positivity constraint on that slack variable. So again, that's what we're saying down here. A couple comments on this. So there's going to be one additional slack variable for each inequality constraint. So you're going to do this for each inequality constraint. Each one then, so if there's M, actually I think it was S, if there's S inequality constraints, then there's going to be S slack variables. So, which is what this says. So the original number of design variables was N, and S is the number of inequality constraints. So the total number of variables now is going to be N plus S, the original number of design variables, plus the number of slack variables that we had to introduce to convert each of the inequality constraints to equality constraints. So the price we pay in effect for having inequality constraints is that we have to introduce a new variable, and that makes our problem bigger each time we do so. Now the slack variables are introduced for each of the inequality constraints, and they become additional unknowns. So that's what makes the problem bigger. Now the total number of equality constraints then is going to be M plus S. So remember, M was the original number of equality constraints in the original problem, and then S is the number of inequality constraints, but we introduce S slack variables to get rid of each of those, and so now we have M plus S equality constraints. So then the total number of variables, which will be M plus S, sorry, this is the number of constraints, is now m plus s, and that has to be less than or equal to the total number of variables, which is n plus s, which of course means that in the original problem, n is bigger than m. That's a linear algebra thing that we'll see as we look at some examples. Now, in linear algebra, we would say that this system of equations is underdetermined. So that means there's not enough equations to fix a unique solution, to determine a unique solution for the problem. So because there's not enough equations, there are an infinity of solutions of ax equals b. So if you just take ax equals b, which are the equality constraints, which now include the inequality constraints, and convert it into equality constraints, there will be an infinity of solutions for that system of equations. Those infinity of solutions define the feasible space that we discussed in the last video. Now, of those infinity of possible points in the feasible space, what we're looking for is the one point that minimizes the objective function. So that's the feasible point. That's the point that we're looking for that is the optimal solution to the problem. So if you look back at our train car example that we had in the last video, we started with n was equal to 2, so that was the number of design variables. That was the number of cars on the first train and the number of cars on the second train, so 2. Then m was the number of equality constraints, which was that the sum of the number of cars on each train had to add up to 100. And then s, for which we have 2, that was the number of inequality constraints, where we had a limit on the number of cars on the first train and a limit on the number of cars on the second train. So n2, m1, s2 in that case. And as you can see, so m plus s is 3, and that is indeed less than n plus s, which is 4. Okay, so the slack variables do not change the objective function. So the objective function is exactly the same as before, even though we have additional variables in addition to the original design variables. Essentially, those c coefficients on the slack variables are just 0. So it doesn't change the objective function at all. It only changes how the constraints are represented in what we're calling the standard form of the linear programming problem. So let's put the train car example into standard form. So we discussed this in the last video. We set it up and we solved it, but kind of in a heuristic way. We just used our intuition to find a solution. So now let's put it into the standard form. So we have the cost function, j, which is 10 times x1 plus 15 times x2. Remember, this was the cost of each train car on the first and the second train, respectively. We had one equality constraint, and that was the sum of the number of cars has to equal to 100. Then we had our two inequality constraints, that the first train could only pull up to 50 cars, the second train could pull no more than 75 cars. And then the positivity constraints that said that each car had to pull some non-negative number of cars. Okay, so clearly everything's fine here with the cost function, everything's fine here at equality constraint, positivity constraints. We have to use our slack variables to take care of the inequality constraints, the two of them. All right, so putting in standard form, here is our objective function. Again, no different than before. You could add plus 0 times s1 if you want, plus 0 times s2 if you'd like, but of course that doesn't make it any different. Then now we have 3 equality constraints, the original one and the 2 inequality constraints that have been converted into equality constraints using the slack variables. So just taking a look at those, so x1 is less than or equal to 50. So that means that no matter what x1 is, between 0 and 50, there's some value of s1 that when you add it to x1 will add up to 50. So again, it's taking up the slack in the x1 equation. So x1 plus s1 is now equal to 50. Likewise, x2 had to be less than or equal to 75. So we add s2 to x2, and that takes up the slack in the x2 variable, such that x2 plus s2 is now equal to 75. So now we have 3 equality constraints, m plus s. 1 plus 2 is 3. And don't forget the positivity constraints. We had the original 2 for x1 and x2 having to be positive, and now we also have for s1 and s2, they also have to be positive. Because if s1 or s2 is negative, then we would have something out that doesn't satisfy the original inequality constraint. So we now have 4 variables. Each variable has its own positivity constraint. So now the vector of design variables includes the slack variables as well. So the vector x includes the x1 and x2 design variables plus the s1, s2 slack variables. So we have gone from 2 to 4 variables. Again, this is n and this is s, capital S. All right, so let's take a look at the feasible space. This is the same problem as we had in the last video, but now it's just expressed in terms of these slack variables. So we'll end up with the same feasible space, but it'll just be expressed slightly differently. So again, 0 and 0 here. We'll go to 75. So this is 75 and 50. All right, so again, remember that, let's see if I can remember to use the same colors. I think I used red. So we had that x1 had to be positive. So x1 is equal to 0 is the left vertical boundary. So it has to be to the right of that. And then x2 equals 0 is the bottom horizontal boundary. So it has to be greater than that. And then we had the, let's see, I forget what color I used for inequality constraints. I'm just going to use blue. So for the inequality constraints, S1 is equal to 0, correspond, well, let me just write it down and then I'll highlight it. And S2 is equal to 0 is up here, that's a 2. So this boundary right here, that is x1 is equal to 50, and if x1 is equal to 50, then s1 would be equal to 0. If x2 is equal to 75, then s2 would be equal to 0. So you see how those correspond to each other. So let me get my colors back here and indicate that. So the S, so again, the feasible space has to be now to the left and below these two S1 is equal to 0 and S2 is equal to 0 lines. All right, and then we have our A and B points as we had before, A and B, which define the original equality constraint. So I'll just add that on there for completeness, but again, what we've done now is express this and this inequality constraint now as a positivity constraint on S1 and S2. Now we can actually put this into matrix form. So remember we had expressed the equality constraints as AX equals B. So now we actually have 3 equations. We had 1 original equality constraint plus 2 inequality constraints, both of which were converted into equality constraints. So we now actually have 3 equations, but 4 variables. Remember, we have to include the original design variables, x1 and x2, plus the new slack variables. So we now have 4 variables. So our system of equations is actually 3 by 4. We have 3 equations for 4 variables, which again is underdetermined. Underdetermined is when there are fewer equations than variables. Overdetermined is when there are more equations than variables. So in this case, we have 3 equations for 4 variables. So let's just walk through each of the equations. The first equation is 1 times x1 plus 1 times x2 plus 0 times s1 plus 0 times s2 is equal to 100. So that says that x1 plus x2 is equal to 100. That's the original equality constraint, which again is saying that the total number of cars on the two trains has to add up to 100. Then the next equality constraint, which was converted from an inequality constraint, says that 1 times x1 plus 1 times s1 has to be 50. So remember again, x1 has to be less than or equal to 50. So that means that x1 plus s1 is equal to 50, where we incorporate the slack variable. Similarly, for the third one, we have 1 times x2 plus 1 times s2 is 75. So that is the equivalent matrix form of the equality constraints. You'll notice that this does not include the objective function at all. All right, some comments about this. So once we put it into the standard form, which again means we no longer have any inequality constraints, only equality and positivity constraints, we might expect that we could just then do like we did for nonlinear programming and differentiate things, set them equal to 0, and go from there. If we had constraints using Lagrange multipliers and so forth, that would be great. Unfortunately, that no longer works, and I hinted at this, the reason for this in the previous video. So if you look at the cost functional 624, so let's go back and look at that. So here it is. So 10x1 plus 15x2 is equal to j. So if you look at that cost function, and if you were to differentiate it with respect to x1 and set it equal to 0, notice what you get. 10 is equal to 0. Oop. Okay, obviously that can't be true. 10 is never equal to 0 in any universe that I've ever visited. Likewise, if you take j and differentiate with respect to x2 and set that equal to 0, that says that 15 is equal to 0, which of course is not true either. So neither of those is possible, so simply differentiating, setting equal to 0 does not work in the linear programming case. And again, it's not a failure of mathematics, it's because in linear programming we're dealing with lines and planes which do not have minimums and maximums other than at infinity, without the constraints again. All right, so we need a more general way to deal with these, and that's called the simplex method, which was developed a number of years ago, back in the 1960s. For solving these, it's still widely used today. There's various variations on it, and we'll discuss that next time.